Okay, let's come back. Let's finish chapter 15. Smart pointers. Yeah. So I've been a long day. But you really want to at least get something done. Because I'm traveling again. So one chapter a day. We're moving slowly but steadily. Okay. RC, what is RC? So reference counter smart pointer. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value may have multiple owners. For example, in graph data structures, multiple edges may point to the same node. Okay. And that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleared up unless there's not even any edges pointing to it, and so there's no owners. You have enabled multiple ownership explicitly by using the Rust type RCT, so that's the smart pointer that allowed multiple ownership, which is an abbreviation for reference counting. RC type keeps track of the number of references to a value. To determine whether or not the value is still in use, if there are zero reference to a value, the value can be cleaned up without any reference becoming invalid. Imagine RC as a TV in a family room. When one person enters to watch TV, they turn it on. Others can come into the room and watch the TV. When the last person leaves the room, they turn off the TV because it's no longer being used. If someone turns off the TV while others are still watching it, it would be an uproar from the remaining TV watchers. We use the RCT type when we want to allocate some data on the heap from multiple parts of our program to read, and can't determine at compile times which part will finish using the data last. So we don't know. We actually don't know who's using it last, but if nobody's using it, then we switch it off or clean it. If we knew each part would finish last, we could just make that part the data's owner, right? And the normal ownership rules enforced at compile time would take effect. Note that RCT is only for use in single-threaded scenarios. When we discuss concurrency in chapter 16, we'll discover how to do reference counting in multi-threaded program, which is way more complicated. RCT is only for single-threaded use. But reference counting is very important for when you have multiple threads. So yeah, that'll be way more complicated, but way more important. Using RCT to share data. We return to our coin list example. Recall that we used the box. Yes, this time we'll create two lists, both share the ownership of the third list. Conceptually, this looks similar to something like that. You have B, and so these two are a different list, but the rest of it is the same. So basically, this one will reference to this one will reference to this one, and they're all the same. We create list A that has the share bits of this. 5 and 10, and then there are two lists that start with 3 and 4. Both C and D lists will then continue to go with the first A list containing 5 and 10. Trying to implement this scenario using list and box, and it won't work like that. So this corns, and then, this is quite normal until here. Then this is the A, and then we use A here. We would have a problem. What problem do we have? We would have that the value moves here because the ownership is passed to here, and this is no longer available. So nope, can't do that. The variants own the data they hold, so we create the B list, and A is moving to B, and then B owns A. So when you try to use A again when creating C, then it's banned. We could change the definition of cons to whole reference instead, but then we'd have to specify the lifetime parameter. By specifying lifetime parameter, we would be specifying that every element in that list will live at least as long as the entire list. This is the case for the element in the list, but not for every scenario. So this kind of work because all of these need to live as long as this, but but it may not. So for this, this will work because this is in the same scope. So yeah, ABC is in the same scope, so it's fine. But what if they aren't? Then it won't work. So change the box to RC. I'll show you in here. So now this will be RC instead of box, and point to a list. So basically more or less the same. And now we have to call clone when we use it. So clone the reference of A. When we create B, instead of taking the ownership of A, we'll clone the RC list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership of the data. So yeah. So what this is doing is actually this will also have an ownership to whatever A is pointing to. So same as C. So now A and B share ownership of that data, and then clone A again. Increase the number of reference from 2 to 3. Now there's 3 owners of that thing. Every time we call RC clone, the reference count to the data of this will increase. And the data won't be cleaned up unless there are 0 reference. Unless all of them are out of scope, then it won't get cleaned up. I need to add a use statement to bring RC to scope. So compared to here, we'll have to bring RC to scope here. Because it's not in the prelude. In main, we create the list only 5 and 10 and store it in the new RC and A. Then we create B and C. We call RC clone function pass. Yeah. We could have called A.clone rather than RC clone, but Rust conversion is to use RC clone in this case. The implementation of RC clone doesn't make a deep copy of all the data like most types implementation of clones do. So that's what makes it different. The RC clone and the normal clone is that because RC clone doesn't make the deep copy. The code, the RC clone only increment the reference count, doesn't make such take much time. Deep copy of data can take a lot of time, and also like memory. By using RC clone for reference counting, we can visually distinguish between the deep copy kinds of clone and the kinds of clone that increase the reference count. When looking for performance problems in the code, we only need to consider deep copy clones and can disregard calls to RC clone. Yeah, so when you're doing like some profiling and like performance comparison, then you know that RC clone is not time consuming. Cloning in RC increase the reference count. So we change the example again and then create and drop reference. So now we make it very complicated. Woohoo! A now is this thing, so we use the reference count of A, so we would do the strong count. And then we create B, and then we do the strong count of the same thing. And then C, same, but C is in the scope, but then like after this C is out of scope, but then we count again. So we see that when we create 1 as 1, B, C 3, but C out of scope, we become 2 again. So function name is strong count rather than count because RC type also have a weak count. So there's 2 type of count. We'll see what weak count is later. We can see that the RC, so preventing, where is this thing? Chapter 15. Okay, we'll see that later. Okay, we can see that the RC list in A has an initial reference count of 1. So this is exactly what this is showing. Yeah, so when we hit here, that would be the drop trait of RC, which will just dereference the count. Yeah, decrease the decrease the reference count. What am I talking about? So what we can see in the example is that when B and A go out of scope, then the count is 0. But we can't see it because that thing is got cleaned up, so it's completely gone. Yeah. By immutable reference, RC allow you to share data between multiple parts of your program for reading only. This is read only though. If RC allow you to have multiple mutable reference too, you may have violated one of the borrowing rules, which yeah, you can't have multiple mutable reference. Multiple immutable borrows to the same place can cause data erasures and inconsistency, but being able to mutate data is very useful in the next session. So what shall we do? There's another thing. The interior mutability pattern and the RC cell type that you can use in conjunction with RC to work with this immutability restriction. So every restriction have a workaround. So how are we going to make it multiple reference but also mutable? So let's have a look. So reference cell and the interior mutability pattern. Interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to that data. Normally, this session is disallowed by borrowing rules. To mutate data, the pattern uses unsafe code inside a data structure to bend Rust usual rules that govern mutation and borrowing. Unsafe code indicates to the compiler that we are checking the rules manually instead of relying on the compiler. So we are going to unsafe territory, which like the compiler won't be there to safeguard you. So this is considered unsafe. Yeah. So if you're using unsafe code, then the responsibility falls back to you because the compiler is not there to help you anymore. We can use types that use the interior mutability pattern only when we can ensure that the borrowing rules will be followed at runtime. Even though the compiler can't guarantee that, the unsafe code involved is then wrapped in a safe API and the auto type is still immutable. So the people using it won't be able to do this dangerous thing. It's wrapped in a safe API. So, but because it's internal, so the person who is writing it, probably you, is responsible. Let's explore this concept by using reference cell type that follow the interior mutable pattern. Enforcing the borrowing rules at runtime. So unlike RC, reference cell type represents single ownership over data it holds. So what makes reference cell different from a type like box? So recall the borrowing rules you learn. So any given time, you can have either, but not both, one mutable reference and any number of the immutable reference. So yeah, so immutable reference, remember we can have a lot of different things. We can only have one immutable reference. But if you have like immutable reference and then mutable reference, and then you can't use immutable reference anymore because because you may change it and then it doesn't guarantee. Reference must always be valid. So with reference and box, the borrowing rules invariant are enforced at compile time. But with reference cell, these invariants are enforced at runtime. So with references, if you break these rules, you could get a compile error. So the normal case, if any of these rules break at compile time, which for example, you call something like immutable reference and you have a mutable reference after, then you would totally be told off after by the compiler. But because this ref cell is checked at runtime, so you can still compile your code. But probably like when you will be able to compile and run the code, but when you run the code, if any rule is broken, then your program will panic and exit. The advantage of checking the borrowing rules at compile time that error will be caught sooner. So the thing you publish is already safe and it doesn't crash the program and stuff. So it's probably more stable. And no impact on runtime as well, because analysis is already done. Checking the borrowing rule at compile time is the best choice in most of the time. That's why it's the default. The advantage of checking borrowing rules at runtime is that certain memory save scenario are then allowed. So if something doesn't work with all these rules, you can try to go to this territory, right? You can check at runtime. When they have been disallowed by compile time checks. Static analysis, like Rust compiler, is inherently conservative, so they are more strict. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the scope of this book, but is an interesting topic to research. Okay, sounds cool. Because some analysis is impossible, if Rust compiler can't be sure the code compiles with the ownership rule, it may reject a correct program. So it may still be fine, right? It's just that the Rust compiler is very straight and doesn't know that actually it will be fine, so you just like reject it, but probably it's still fine. In this way, it's conservative. If Rust accepts an incorrect program, user won't be able to trust the guarantee Rust make. However, if Rust reject a correct program, the programmer will be inconvenienced, but nothing catastrophic can occur. Yeah, basically it's a workaround. Rust cell type is useful when you are sure your code follow the borrowing rules, but the compiler is unable to understand and guarantee that. Similar to RC, reference cell is only for use for single-threaded scenario and will give you a compile time error if you try to do a multi-threaded context. We'll talk about how to get the functionality of a reference cell in a multi-threaded program. So there's like always something more to learn, right? Like at the beginning, it's like you can't have multiple references. Like, okay, now learn about RFC, you can have multiple reference, but they're immutable. And I was like, but we want mutability. I was like, okay, now learn about this like internal mutability and reference cell. It's like, okay, but then it's only for a single threaded. And then you're like, but I want to do it in multi-threaded. Then we'll talk about it in chapter 16. But it's like always like if you want to do a little bit more, then it's like, okay, you have to learn more. So recap. RC enable multiple ownership. Box and reference cell will have single ownership. Box allow immutable or mutable borrows. Check at a compile time. RC allow only immutable borrows. Check at a compile time. A reference cell allows immutable or mutable borrow. Check at runtime. Because a reference cell allows mutable borrows, check at a runtime. You can mutate the value inside reference cell even when reference cell is immutable. Interesting. Oh, I got something in my eyes and now I feel very uncomfortable. Mutating the value inside the immutable value is interior mutability pattern. So reference cell itself is immutable, but you can mutate the value inside. Let's look at a situation which interior mutability is useful. So when you have an immutable value, you can borrow it, for example, like this. So this is x, n mu x. So if you compile the code, you will have something. You have something wrong because x is not mutable, right? However, there are situations in which it will be useful for a value to mutate itself in its method, but appear immutable to the other code. Code outside the value's method could not be able to mutate the value. So probably if your compiler checked, it was complain to you because you changed something that is not mutable. But if it's checked at runtime, since you change it inside, so you can kind of get away with it. Using reference cell is one way to get the ability to have interior mutability. But reference cell doesn't get... Interesting. Doesn't get around the borrowing rules completely. Borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at one time instead. If you violate those rules, you will still get a panic and it will still won't work. Let's work through a practical example where we can use reference cell to mutate an immutable value and see how it's useful. This is getting more and more complicated, man. Yeah, sorry, my eye is really getting me. Like, I was outside and something blew inside my eyes and it's really hurting me. A use case for interior mutability, mock object. Ooh. We also have mock object in Python. Sometimes during testing, a programmer will use a type in place of other types in order to observe particular behavior, and then insert is implemented correctly. This placeholder type is called a test double. The thing of it is a sense of stun double if we make yeah. So it's something that mimics the other thing. Where a person step in and substitutes for an actor to do particular tricks. Test double stands in for other types when we are running tests. Mock object has specific types of test doubles that record what happens during a test, so you can assert that correct actions took place. Yeah, we do have mock object in Python. It's in your standard library. So yeah, that's extremely useful when you have some like external thing and you want to do some unit testing. You can just like take care of that instead of calling the API or something like that by mocking it. Rust doesn't have object in the same sense as other languages have object. So in Python, it's more straightforward. Rust doesn't have mock object functionality built into the standard library as some other languages do, like Python. However, you can definitely create a stun that will serve the same purpose as a mock object. Okay. Here's the scenario we'll test. We'll create a library that tracks a value against the maximum value and send message based on how close to the maximum value the current value is. The library would be used to keep track of a user's quota of the number of API calls they are allowed to make. For example, our library will only provide the functionality of tracking how close to the maximum value is and what the message should be at what time. Applications that use a library will be expected to provide a mechanism for sending the messages. The application should put a message in the application, send an email, send a text message, whatever. The library doesn't need to know the detail. All it needs is something that implements a trait that we call messenger. So, trait messenger, send limit tracker is the struct. So we only have the maximum and the value size, and we'll take a messenger. So it's like T. Here's a messenger. So whatever that has the messenger, that's fine. The lifetime is the same as like how long the messenger leaves. Then we implement the new. Just do this. Limit tracking. So set value is percentage of max, so we know how much maximum has been used. So if it's bigger than 1, you're over your quota. If it's quite close, bigger than 0.9, you have used up 90%, otherwise like 75%. So they're giving some warnings, urgent warning. Important part of the code is that messenger trait has one method called send that takes an immutable reference of self and the text of the message. Here. This trait is in the interface. It's the interface our mock object needs to implement so that the mock can be used in the same way as the real object. The other important part is that we want to test the behavior of set value at limit tracker, we need to change what we pass in for the value parameter, but set value doesn't return anything for us. Make a session. You want to be able to say that if we create a limit tracker with something that implement that message trade and a particular value for max, then we pass different number for value. The messenger is told to send the appropriate message. So we need a mock object. Instead of sending an email or text message, we call send. We only keep track of a message that is told to send. We can create a new instance of that mock object. This is our test. This normal thing in the test. We have mock message. So mock message, we have send message. It's a string, and then we have mock message. So new, we would give back a mock messenger that's only do send message. So messenger for mock messenger is the send, this send here. So this mock object is look very similar to this, but what it does is just that it will keep a send message there. Yeah, so what do we want to do? So when we test it, the mock message equal to this new, and then mu limit tracker equal to limit tracker. This is the real one, but we will give it a mock messenger, and I give it a value 100. So limit tracker dot set value is 80. So then we will check whether the mock message send message the length is 1. So that we have a problem here. What? So yeah, we'll hold the back of string. Keep track of the message that is told to send. We also define a associated function new. The messenger trait for them, so we can give him. Yep. So send method, we take the message, pass in as a parameter, and store it in the. So instead of send, we will just store it in the send message here. No, here, send message here. In the test, we test what happens when limit tracker is told to set value to something that's more than 75 of the max value. So if it's more than 75, we probably will have a message. That's why we should have one message, right? Because that yeah, we have one message in it, but we have a problem. It won't compile. Because so in here in send we have borrowed the self-reference. We can't change it because yeah, it's a immutable reference, but then we are doing something. We're changing this. So it's probably not allowed. Send method take an immutable reference to cell. We can take the suggestion from interior text to use mu self instead. So this is saying like, oh, so this is not mutable and you can't. So maybe you should use, yeah, maybe you should use mu self. Because the signature of send won't match in the messenger trait definition. Because the original design is not supposed to change, right? It's supposed to be self and then do whatever, like sending the message stuff. So no, you can't do that. Yeah, or you can try to. You would get another error message. So now it's like we have a chicken and egg problem. So we really can't do that. Like, you know, yeah, so what should we do? Then now, of course, we can use what we've just learned. There's a situation where interior mutability can help. We'll store the send message within a reference cell, and then the send method will be able to modify the send message to store the message we have sent. So this time we will use the reference cell, and we'll store this in the reference cell. And then now, so when we create a new one, we will create a new reference cell here. But then this time, send message we would call borrow mute, and then push. So now this time we have that instead of just vex string, and then we'll create new of those as well. For the implementation of the send method, the first parameter is still an immutable borrow cell, which is fine. Then we call borrow mute to get a mutable reference to the value inside. So the value inside here is vex string. So now vex string is mutable. Then we call push to immutable reference to keep track of the message sent during the test. The last change we have to make to the assertion here is that we will make a immutable borrow to it. So immutable reference to the vector. So now it will work. So keep track of borrows at runtime. So now we can create immutable and mutable reference at the same time. So normally use n and mmute, but with refcell we use borrow and borrow mute, which is part of the save API that belongs to refcell. Borrow method returns the smart pointer type ref, and borrow mute returns the ref mute. So both type implement deref, so we can treat them like regular references. The ref cell keeps track of how many ref and ref mute smart pointers are currently active. Each time we call borrow, the ref cell increase the count of how many immutable borrows are active. When a ref value goes out of scope, the count of immutable borrows go down by 1, just like the compile time borrowing rules. So that's how the rule got implemented inside. Ref cell can tell us, let us have many immutable borrows or one mutable borrow at any point in time. So these rules are still upheld. You can't have the mix of both, but it got checked at runtime by refcell. If we try to violate those rules rather than getting a compile error as we would with references, so if any rule is broken, then refcell just throw a panic at your face. So modification of implement send. So if we do something silly, so we do 2 mutable borrows, then yeah, you will probably get a panic. You got panic. Yeah. Failure. So it got pancaked. So yeah, it can't. The code panic at message already borrowed. Borrow mute error. Choosing to catch borrowing errors at runtime rather than compile time means that you potentially will find a mistake in your code later in development process, possibly not until your code was deployed to production, which is not good, because someone may suddenly run your program and it got crashed at some time, which is not very nice user experience. Also, your code would incur a small runtime performance penalty because ref cell is basically keeping track of things. That's the overhead of doing that. However, using ref cell makes it possible to write a mock object that can modify itself to keep track of the message it has been been sent while you're using it. So there are trade-offs. So most of the case, if you can, use the normal thing, but if you have to break those rules, but you know what you're doing, use ref cell. have multiple owners of multiple data by combining RC and ref cell. Common way to use ref cell is combine with RC. Recording RC will let you have multiple owners of the same data, but you are only allowed to do immutable access. If you have an RC that holds a ref cell, you can get a value that have multiple owners, and you can also change it. For example, the con list example before, we use RC, so you can put like A and B and C, right? Yeah, because RC only hold immutable values, so we can. So if you add ref cell, so add another wrapper, to gain the ability to change the value in the list. So this is what it looks like. Ooh, very complicated. Oh my god. So value is RC new, and then now we have ref cell as well. New 5. So A would be cons. We will clone the value. Oh my god. So you have to also wrap the value. And then RC new, and then you put it there. So every time you have to wrap it in ref cell and then RC. Oh my god. Of course you have to clone it like you do with RC. Yeah, now you can mutable borrow the value. You can change the value, and then everything got changed probably. So you print it out, you add 10 to it, so it will be 15 instead of 5. Oh my god. Yeah. Why? Why we do that? Yeah. What's the error operator? Oh yeah, this is the referencing it, and then yeah, change the value of it. This technique is pretty neat, yes, but it's very difficult to look at. It give you, like, if you're not used to this, it will give you a heart attack. We have an originally immutable list value, but we can use method as ref cell to wrap it. So now you can access in interior mutability as we modify our data when we used to. The runtime check for borrowing rules protect us from data raised. Is sometimes worth trading a bit of speed for this flexibility if you need to. Notice that ref cell does not work for again, it doesn't work for multi-threading. If you want to know how to do that, read chapter 16. We also have another thing. Yeah, this is called mutex. It's for multi-threaded code. It's the thread safe version of ref cell. Mutex. We'll discuss that in chapter 16. We'll learn about that. Okay. Last part of this chapter. Reference cycles can leak memories. Ooh. Rust memory safety guarantee make it difficult, but not impossible. So if you try really hard, you can break it. To accidentally create memory that is never cleaned up, which is memory leak, which is something we don't like. Preventing memory leak entirely is not one of Rust's guarantee, meaning memory leaks are memory safe in Rust. We can see that Rust allow memory leaks by using RC and ref cell. It's possible to create reference where items refer to each other in a circle. This creates memory leaks because the reference count of each item in the circle will never reach 0, and the value will never be dropped. So it's still memory safe, considering like it's just a bunch of junks that's hanging around in the sky in the memory pool, but it's still memory safe because the insecurity is that when you access some memory that's out of scope, right? But yeah, it's just not very good. It's a memory leak. Well, it's just what it is, but let's see how we can break Rust. So let's look at how a reference cycle may happen and how to prevent it. So yeah, learn how to break it so you can prevent that. So we have list, which is our conf list. We have RC and ref cell. This is a bit fishy because we did it the other way around at the other example, right? So here we have function called tell, and then we may output this match self. So if self is conf list, then return some item. If it's nil, then none. Okay. Instead of having the ability to modify the i32 value, we now can modify the reference. We want to modify the list value a convariant is pointing to. We also adding a tell method to make it convenient for us to access the second item if we have a convariant. Yeah, this is getting the second item. So if it's new, then it's none. Adding a main function that use definition. This code now create. Oh, reading that again. Okay. Yes. Okay. So now we have A, which is a RC colon 5 reference cell new and an RC. So now the initial reference count. So we see, and the next item is a.tell. And B will create the here. Let's some. Ooh. And come in the rest. I see that we have cycle. It's overflow this. It will overflow the stack. Are we going to run this code? You sure? Okay. Stack overflow is coming. Woohoo! Right. So. Okay. So now we have A. And then B, we create B. So we also keep track of the reference count. A.tell. So we access the A.tell, which is the second item in A. And then so this link will make a mutable borrow and then put B in it. Oh my god, yeah, it's a circle. Oh my god, what's going on here? Yeah, can someone draw a picture, draw a graph of what's going on? What's going on in here? So A.tell is supposed to be this new thing, but then we change it to B. Oh my god, let's run it. Yay! So A initial RC count is 1. A next item. So next item will be the new one, the new cell. So and then B after count after B creation is 2. So initial RC count for B is 1. So B next item will be this thing. And then after changing A, the B reference count is 2. Yeah, so they just point to each other. We create an RC list instead of holding a list, but in variable A with an initial value of 5 and new, we create RC list instant holding another list value in the variable B that contains the value 10 and points the list to A. So we modify A so that it points to B instead of new, creating a cycle. We do that by using the tail method to get reference to the second item in A, which we put in the value link. Then we use borrow mute method to change the value inside to hold that hold new in, and now is to hold B. Oh, when we run this code, the last print line comment out, because yeah, ANIX item, this will okay, because this will create the Stack Overflow. Because this try to access the second item, and then it will go to B, and then B need to go back to find what is A, and then it would just go on and on and on and on and on. Yeah. Whoa. Oh my god. Oh, so A is this, and then you try, so B is this, and then it just creates this loop. So A is this, B is this, and then you change B into holding B inside, but then B is holding A inside, and yeah. We'll get this. So the reference counts for both A and B is 2, because after we change the listenates at the end of main, Rust will drop variable B, which will decrease the reference count of B from 2 to 1. The memory that RC list has no heap won't be dropped at this point, because its reference count is 1, not 0. Then Rust drop A, which dereferences the reference count of A from 2 to 1 as well. Now, yeah, it would drop B, but then A is holding B, so A is holding this one reference, but then it won't get dropped because there's still 1. And now you drop A, and yeah, so now A and B still have 1 reference, so they would just be there, even though we can't access them because A and B is dropped. This instance memory can't be dropped either, because yeah, the memory, so we will drop this to A and B, but this loop will be floating in memory forever. The memory allocated to the list will remain collected forever. So if you uncomment the list, print list, and run the program, Rust will try to print this cycle with A pointing to B, pointing to A, and so on and so forth, so it will have a Stack Overflow. Compared to a real-world program, consequences of creating a reference circle in this example aren't very dear. Right after we create a reference circle, the program ends. Yeah, so when the program ends, everything created within the program get destroyed. So this will be destroyed, probably by your operation system. However, if a more complex program allocates lots of memory in the circle and held onto it for a long time, the program would use more memory than it needs and may overwhelm the system, causing it to run out of available memory. So either your program will run very, very slow because there's a lot of swap that need to be done, because a lot of memory in the heap has been used up. So you would get very, very slow, or worst case scenario is just crash your whole thing. So creating a reference circle is not easily done. You can see how clunky this is. Oh my god, this is giving me a headache. But it's not impossible either. You can, if you try really hard, you can break it. Come on. If you have reference cell, a value that contains an RC value or similar nested combination of type with interior mutability and reference counting, you must ensure that you don't create circles. You can't rely on Rust to catch them. Creating a reference circle would be a logical bug in your program that you should use automated testing, code reviews, and other software development practice to minimize. So yeah. Another solution for avoiding reference circle is recognizing a data structure so that some reference express ownership and some reference don't. As a result, you can have circles made up of some ownership relationship and some non-ownership relationship. And only the ownership relationship affect whether or not a value can be dropped. So in this case, because A, B both have ownership, inside A and inside B, they both have ownership, so that's a problem. So if you sometimes not having ownership is a good thing. We always want cons value to own their list, so recognizing the data structure isn't possible, let's look at an example using graphs made of parents node and child nodes to see what non-ownership relationship are appropriate way to prevent reference cycles. So, now we're calling the week thing. What have I done? Okay, we just moved. So now turning a RC into a week. So far, we've demonstrated that calling clone increases the strong count of RC reference, and then RC instance only clean up if strong count is 0. You can also create a weak reference. So instead of strong reference, which is a clone, which have ownership, you can also create a weak reference by calling downgrade and passing a reference to LCT. So instead of clone, it's the downgrade. Strong reference are how you can share ownership. Weak reference don't express an ownership relationship, so it's kind of like a borrow, and it counts doesn't affect when LC instance cleanup. They won't cause a reference cycle because any cycle involving some weak reference will be broken once the strong reference count of values involved is 0. So no matter how many weak reference you have, once the strong reference count is 0, they will get destroyed. When you call downgrade, you get a smart pointer of type weak instead of increasing the strong count of RC increased by 1. Calling downgrade increase the weak count by 1. And RC type use weak count to keep track of how many weeks reference it exists. Similar to strong counts, the difference that weak counts doesn't need to be 0 for the RC instance to be cleaned up. Because the values that weak reference may have been dropped, to do anything with the value that a weak T is pointing to, you must make sure it still exists. To do this, you can call upgrade method on a weak instance, which will return an option. So you either get a result of sum of that RC value that you, if it hasn't been dropped, if you still can upgrade it, then you get something back. You will get a sum. You will get none if the RC value has been dropped, so that thing doesn't exist anymore. Because upgrade returns an option, rest will ensure that some case and none case are handled. So you have to use the pattern matching again, and there won't be an embedded pointer. So yeah, so now it will just give you a none case so you can handle it, so it won't crash your program. As an example, rather than using a list whose item knows only about the next item, we'll create a tree whose item know about the children item and their parents item. So this is another data structure. It's a tree data structure, a node with a child node. So now we have a node, we have a value, we have a children, which is a ref cell, so this can be changed. But now we have a vec of RC, so it will be a list of things, and each of them is a reference to a node. We want a node to own its children, so if it's the children, we want to share the ownership with variables, so we can access each node in the tree directly. To do this, the vect items to be values of the type RC node, we want to modify each node of the children of the other node, so we have a ref cell, so we can also change the children. Next, we'll use our struct definition and create one node instance named leaf with the value 3 and no children. Another instance named branch and have value 5 and the leaf as one of its children. That makes sense? We'll clone it because this is a strong reference. We want to be able to own it. We clone it, store it in branch, meaning that Nook and leaf now have two owners, leaf and branch. We can get from branch to leaf through branch to children, but there's no way to get from leaf to branch because leaf has no reference to branch and doesn't know they are related. But now we want leaf to know branch is its parents. We will do that next. So adding a reference. So this time, children Nook are aware of its parents. We'll add a parents field to the Nook structure. The trouble is that the type of parent, deciding what type of parents would be, we know it can't be certain containing an RC because that would create a reference cycle. It's the same problem with leave the parents pointing to the branch, and then they will point back to the children, and again it's so strong count value will never be 0, so it's the same scenario. Think about the relationship the other way. So a parent's note would own his children. If a parent's note is dropped, his children's note should be dropped as well. However, a children would not own his parents. So if we drop a children's note, the parents should still be fine. So in this case, we can use a weak reference. So we'll, to make the type of parents, use weak T. So we would use weak instead, not using RC. So it look like this. A note will be able to refer to his parents, but it doesn't own his parents. We would change main to be like this. So yeah, so we have leave is this, and then if we want to find the parents, we would do the dot upgrade. Remember, we should probably also handle the none cases as well. But we are debugging, so we just see a none here. Yeah, so if parents, what are we doing here? So branches, we have parents and children, leave the parents, the borrow mute. So this will be branch, and then we'll borrow mute, and then so the what is this doing here? Like branch. So I clone the leave, but this hasn't been linked yet, right? So this one I'm linking them. So I'm putting. So I'm calling the parents here. So this I can change this because it's ref cell. So I will borrow mute, and then now I would make a weak reference. So I would call downgrade of the branch here. So now these two are linked. So now you will see that they will print out something. So this will print out probably the branch. So before this will be none because it hasn't been linked. I don't know. It is the first print statement, yeah, none, and then the second one will be some note value 5 parents would be this one. Some is a weak reference here. I got a sum variant, so there will be sum of the branch. Now leaf can access parents. Avoid the circle that eventually end in the Stack Overflow like we did. Yeah, because it will be weak instead. It won't go try to find it. The lack of infinite output indicate that this node didn't create a reference cycle. We can also tell this by looking at the values. So now, if we want to look at strong count and weak count, so yeah, we have a similar thing. We'll create the leaves. We would print out the strong and weak count, and then create a branch. Link them up, and then print out the branch and leaf. And then now branch go out of scope, and then we can see the leaves again. So let's run this. So we create a leaf, so we have this. So we have strong reference, 0 reference, one strong reference, no weak reference. Now we create a branch and link them up. So branch will have one strong reference, one weak reference, because the strong reference will be this, and then after it linked it up, so we have a one weak reference by the leaves. So leaves now we have two strong reference because it's itself and also its parents is having strong reference. And then leave parents. So after these two, so now it's out of the scope. So the ooh, sorry. So yeah, now it's out of the scope. So we don't have the leave parents anymore. There's none. When we upgrade, we got nothing. Ugh, sorry. Just want to sneeze so much. reference can't go back to what it was. So, oh, that's what I. Oh, I'm sorry, I should end soon. I'm sneezing and snoring and okay. So, right. So we don't, because like this is weak reference. It's not like symmetrically like linked to each other, so we won't have a circle. The chapter cover how to use smart pointers to make different guarantees and trade-offs from those Rust. So we have learned a lot of things, and we play around with lots of pointers like box, RC, ref cell, and weak. Yeah. So yeah, deref and drop very important. And want to implement your own smart pointers. Whoa, what is this? This is another thing. Wow. Okay. I don't think I'm implementing my own smart pointer anytime soon, so we will come back in the future. This is very complex topic. Yeah, again, like it looks very scary if you're not used to it, but I guess if you have dived into it long enough, then it doesn't look so scary. It's just like everything else. So I think I'm done. Like I said, I'm sneezing, I'm like, yawning, and I'm very tired. So I should probably end it today here. We have 1, 2, 3, 4, 5, 6. So well, appendix doesn't count, I think. So 5 chapters and and half of the rustling exercises. So not too bad. Yeah. We are at least like, I think we only have 1/4 of the book left. They are very difficult, but it's doable. And then is it half, or maybe no? I think it's quarter. Maybe it's quarter. Quarter of the rustling exercise left. I can't remember how much we have left for the rustling exercises. Does it show? Maybe it doesn't. Yeah, it's just a bunch of other things. I forgot how far we go with the rustling exercises. Oh, doesn't matter. Yeah, we will figure it out. And thank you so much again. I have to continue tomorrow and we'll do concurrency, another very very mind blending topic of such. Yeah, so I will see you tomorrow. Bye.